Jessica? So you did this?
I did the 3D model, but since I don't have this laptop, I cannot do the JSON, so I asked Victor to do it.
Someone did it for you?
Victor.
Victor? Aha. Then I have to make sure that he did the right thing. Okay, anyway, I will check it. But yeah, I'm not quite sure if it is the right thing. Let me remove this filter. So now we have two meshes. And let me load it again. Yeah. Now we have this. Is this for group A or group B? So let me download group C. Oh, I shouldn't press this button. Okay, so actually I think Victor did it correctly. Yeah, this is for group A. This is for you, yours. It is right. But somehow I don't see group V. Okay, anyway. Right?
It's different.
It's different from yours?
It's group C's.
This is group C. Okay. Okay. Okay, this is group C. So I think Victor didn't do it correctly. Okay, anyway. Okay. Now I want to show you how to work on this structure. There is a file. If you go to Model, I have two files, and make sure that you get the Grasshopper file. One of them is Rhino. I think the second one is the Rhino file. The first one is Grasshopper file. And I want you to start from scratch. So you start from an empty Rhino file. Right? This is an empty Rhino file. And if you open this Grasshopper file, okay, you may have some missing component, because I'm not sure if your machine has installed a plugin called Human. So this one is from Human. Okay, if you don't have it, you neglect it. It is okay. I mean, then you cannot use this one. Okay, but I will show you from my machine how this works and how you can make use of it. Okay, and later you can install Human on your machine or on the machine here, then you can use it. Okay, so now I want you to I want to get information for this existing mobile structure. So first I would like to make a reference. So go to File, Workstation, and then attach. Okay, the file I want to attach, you can get it from load 100 model. I think last time I have showed it to you. So now we have, it is gone. It is removed. How come? Is it because, okay, it because of the folder. Okay, that's okay. So as I go back to grid view, yeah, here, you get this file, okay, and then you attach it. Okay, let me do it. Let me do it. Sorry, this one, 3D model. So I download it. Takes a while because it's kind of large. Okay, it's done. So I go to Rhino. Okay, so if you can open the folder, you find this file, you can drag it. This one, Mobius. You can drag it and put it. Then you get this window. I think last time we have done this, right? But you have to select attach file because I want you to know how to make use of references. Then you click OK. Okay, so this is it. And if you go to this layer window, then you can see that this reference file, here you find a hierarchy of layers. The top level is, I think it's the same as the file name, Mobius.3dm. Okay, and you can turn on and off all these sub-layers. Okay, so there are 4 layers. The last one is a mesh. We don't need it, close it. The first one is the surface, the entire surface. Okay, so we have many different things. So we close the surface, close the zones, and we keep only the breadth. Okay. I am not quite sure why we have these lines. Let me also turn off this line. Okay, now the lines are from the other attachment. Okay, so we go back to the grasshopper. Okay, this grasshopper script is to retrieve necessary information for you to go on, okay, for your design and fabrication. Okay, and this one is to select object. Okay, and you want to display information regarding this set of object. For example, if I select all of them and then I click this button, sorry, doesn't work. I think I should use a button instead of this one. it is correct. Doesn't reading anything? Why is that? Oh, okay. Okay, I know. If this is a true Rhino geometric entity, then this should work. This should work, but it is reference. So for example, if I draw something here, okay, and I select it, okay, and then I click, okay, then you get the section, okay. So this component is supposed to retrieve whatever you have selected in your Rhino canvas, but it works for the true Rhino entity, and these are not. This is reference, okay. So you cannot do anything on it. You cannot move it, but you can access it. Okay. And now I have to reference this spread to all the surfaces. How come I? Sorry, the machine is not quite listening. Okay, and then what? And I said, hey, what's wrong with it? Okay, now I set this spread to all the surfaces. Okay, and this one is called object attribute, and you probably don't get this one because this is from human. Okay, I cannot release my mouse button. You see here, this arrow pointed here. This is the human plugin. So if you install human, then you get this. And the purpose of it is to visualize the information inside each of this entity. Okay, so you see every panel on this mobile street has an ID. So this is the ID. Okay, and the ID, if you take a look from this Rhino canvas, oh, sorry, doesn't quite work. How come I cannot see it? Okay, so if I select it, and show the property of it, sorry, I think there is something wrong. Okay, let me start a new Rhino. Large object. Okay, and what? Why? Sorry, I think I have to terminate it and start it over again. Okay. Rhino. sketch file. Okay, and go to layer. Open all the sub menu, sub layers, and turn on only the bread. Okay, and then you don't show all the others. Okay, and now we need grasshopper. Okay, so now we can select everything and then make reference. Okay, and let me show you. So if I select one surface and then we check the property of it, you see there is name. Okay, it is all grayed out because it is referenced. So you cannot change anything. But you can see the information inside this geometric entity. There are many different things. They are all properties of this geometric entity. And there are layer, okay, and there is a name. Okay, so somehow the modeler, the person who built this model, used the name to assign an ID for each of the panels. And this component from human is capable of retrieving this information from objects. So here you input all the object, can be breadths, can be meshes, can be whatever geometric objects, and then it will access name, layer, and what is FB? Layer full paths. Okay, because a layer can be hierarchical structure, and this is the color, material for rendering, and line type, group indices, because this object can be in a group, even a nested group. And this is plot weight, when you want to plot the drawing, what is the line weight of it? And plot color, it can be different from the color that you display on the screen, whether it is visible or not. And what is UDK? User data. Okay, you can have user defined data, and there are keys and value. Okay, so if you want to write a program to access information in these Rhino entities, maybe this component will help you a lot, because you can use this, especially this user data. You can store a lot of information that you need. Okay, and in our case, we want to figure out which panel is which. Okay, so we can use this to see the ID of each of the panel. Okay, and now we have all the panels, and for example, we need to identify all the joint, right? We need to get precise location of each of the joint. Otherwise, when you design your panel, you don't know if it is okay, if it fit exactly correctly onto this joint, right? Remember the structure, we have joint on the intersection of grid, and all the structures that you design eventually has to fix onto this grid intersection, right? So we need to know precisely the location, the coordinate, and the dimension of this. Okay, so first we derive this information from the design model. Okay, and there are other problems, but we start from here. So here, first we get all the edges from this breadth, okay? We find the endpoint of all of them, and then we merge, sorry. Is this right? No, this is not right. I think I loaded in the wrong file. Okay. Open. Sorry. Okay, this is correct, sorry. But is it the same as the one you download from Moodle right now? Is it the same one or? Yeah, okay, that's right. Okay, then that's good. So we have all these breadths, and then we find the edges. These edges, the top one is the naked edge, which means the boundary of these edges. I think because each of these, at least for most of this breadth, they are all this kind of rectangular quadrangles. Okay, most of them, and there are no interiors. How come? Oh yeah. Mostly they don't have, but there are some of them. Okay, I will explain later. Okay, and for all the naked edge, which means the boundary of these panels, then for each of them we get the starting point, the end, and the end point, and we make a line on it. Why? Because we want to replace all these curves into a straight line segment. Okay, and we joint them into a single polyline for each panel. Find the control point of them. Okay, because we want to make sure that the order is correct, and each of these quadrangles, actually you find 5 points for each of them, because it repeats the first point. So if you take a look at this, most of them consist of 5 points. And if you check the coordinate, you see the first point and the last point are the same position. So here we call the last point. So with index -1, you remove the last one. So after you have done this, most of them become 4 vertices. Okay? And what we want to do, we want to find out the crosses. Why is that? Okay, now the structure has been built, right? Are you sure that the design model perfectly match the constructed structure? No, right? So what can we do? Now we are going to fabricate what we design, and we want to install whatever we design, we fabricate it onto the existing structure. So what happens if they don't match? I mean, the built structure and the design model, if they don't match, then what happens? the panel you fabricated are useless, right? Because they don't match. So what we need to do, we have to measure all the critical positions of the existing structure and then use that corrected measurement to fabricate. Okay? Now we may use the design model as a reference. So we can design and then we can discuss how we want to dissect it. But at a point when you want to fabricate it, you cannot fabricate based on the design model because it is not going to match the existing, the built structure. So now for each panel, first I convert all the curves into straight line segment and find all the diagonals. Why I want to do that? Okay. Because if you go to the mobile structure, I mean, we cannot measure the whole thing. It is impossible, especially it is a curved structure. But what we can measure, because what we concerns are the joint, the intersection of grid, right? If we make sure that the distance between two neighborhoods, I mean the two consecutive intersections, we know exactly the distance, especially the four vertices of each quadrangular panel. Okay? We need to make sure that the relationship between these four vertices are very precise. Then we can use this to design our panel. Whatever shape we design, we know that these four vertices are the points where we can fix the entire panel onto the structure. So we need to be very sure about this. So what we can do is we go to the site and measure the distances between neighboring vertices. Okay, we are not able to 3D locate, right? We cannot find the coordinate of each vertex, right? But we can measure the distance. Okay, so for each quadrangle, how many distances we need to measure? This one, this one, this one, this one. Is that enough? No, right? Because even if we know exactly the length of these four edges, we still don't know exactly what is the shape. We need to measure the diagonals, right? And especially these four vertices may not be planar. They are not sitting on a plane. They can be twisted. Okay? So these two diagonals, they may not intersect. Their relation can be like this. Okay? But if we measure all the distance of these 6 lines, then we use this to design your panel. Okay? Your panel can be like this. Okay? It doesn't matter if it fits onto the boundary of this panel. I mean, it can be like this. Okay? And the next panel can be like this. Okay? Whatever shape you have. But you know that at this, sorry, not this one. This one. At this location, this one are the locations where you can fix your panel onto the structure, the laminar structure. Okay? So now what we need to do is for each group, you need to go to the job site and measure the distances for every quadrangles. not necessarily for quadrangle. And what happens if this is a pentagon? If the shape has 5 sides or 5 vertices, then how many measurements do you need to take? Okay, so we need to measure full relationship between all these vertices. Okay, so of course the boundary, 5 measurement, this one, okay? So this is the 0th vertex, this is the first vertex, and this one, also this one. And how about this one? You need to go this one. So you have 5 edges plus 4 edges plus 3 edges plus 2 edges plus 1 edge. You need to take 15 measurements for a pentagon. Okay? And for a hexagon, you need 21 measurements. Okay? In order to make it very, very precise. Okay, so also from here, I would like you to be aware that in a real construction project, you also need to do that. Okay, for example, like the Taipei Dome. Okay, they have designed all these panels based on architects' drawing or model, right? But then after the construction company, after the general contractor build the structure system, they need to be aware that the built structure is not exactly the same as the design model. Okay? It never gets so perfect. So they have to do the measurement. Okay, or the structure or the envelope system they design is able to take the displacement. Okay, maybe the system that you design is very flexible, so that when construction team try to install these panels, they can adjust on site. Okay, and then regardless of the displacement of the actual structure built and the design. Okay, but in the cases of curved structures, then this problem becomes very, very critical. Okay. So whatever you design, okay, and for every panel or every piece you want to fix onto the structure, you need to make sure that the location of this joint are handled. Okay, so each group you need to go to the job site and then make measurement, and then you have to manage this information. Okay, you see how many measurements you need to take. For each panel, you have 6 measurements. Okay, and there are some situations more complicated because not all of them are quadrangle. Like this one is pentagon. Okay, so you have more to measure. Okay, and the idea is that actually we can store all this information into our database, like this one. Okay, but I think maybe we are not able to practice that. But I want you to have this the concept. So this database is supposed to store the information for design and fabrication. So if the database is designed adequately, then we can also store the information of this measurement, okay, and share this information with all participant. Okay. And this Rhino, this grasshopper file, oh sorry, I pressed the wrong place again, and it is opening another Rhino. Okay, and here it simply try to create all required measurement and display it as lines. So if you highlight this, then you can see that all the diagonal here, okay, all the diagonals, and it getting very complicated when this is when it is more than 4 sides. For example, this is a pentagon. So you see these star-like patterns. Some are very weird because some of the panels has very close vertices. And some panels, actually, for example, like this panel, consists of more than, no, not this one. Because this is a Mobius strip. So at the joint boundary of this Mobius strip, strange things happened. Okay, it's because of this joint. Okay, it's because of the computer graphic thing. Last week, I think I showed you how to dissect this Mobius strip, right, into zones. So I use a rectangular area to reference to this Mobius strip, okay? But for Mobius strip, actually, we have to join. After we rotate 180 degrees, then we join the two surfaces, right? Let me show you this way. For the Mobius strip, we rotate 180 degrees and then join. Okay? So in computer graphics, it also does it exactly like this. So this side is rotated 180 degrees and then join this side. So on our model, you see this seam here, okay? Which group, which team is so lucky to get this area? Here, this is a seam of this Mobius strip. You have any idea which team?
I think there will be 2 teams.
2 teams, okay, so you are lucky because this is more complicated. When you select the panel, you see, this is not one surface, but a poly surface, which means it consists of more than one surface, okay? But in reality, it is not so complicated, but when you want to use a computer program to analyze this, then it causes trouble. Okay. Okay, anyway. So this is a grasshopper script. I did it, and I'm thinking maybe it can help you to analyze it. Okay, so for example, for this panel, okay, for this panel, there are 0, 1, 2, 3, 4, 5, there are 6 vertices, okay? And for these 6 vertices, this program creates 21 lines to connect all the interrelationships between them. But this one is, okay, I think this one you don't need to do it so complicated. Maybe you just assume that there are only 4 vertices and then you measure the 6, you take the 6 measurement. But because we use Grasshopper to analyze the geometry, so this panel is divided into 2 parts, and there is no way to join them into one single surface. Okay, I have to say, yes, there are ways to do that, but it is not so straightforward. Okay, but for all others, if you slide this one, the index, then you can go to some other panels. Okay, for example, like this one. Okay, so you get this one and then you find the coordinate of them. Okay, and then you can calculate all the distance between all these vertices, and then if you go to the job site, and also from the other, okay, let me see, from this one, you see the ID of this panel, right? And you see all the vertices, and then you make measurement, and then you have to record it following maybe the indices of this panel. Okay, and also the ID of this panel. I mean, somehow you have to put it down and make sure that every information is correctly referenced. You know what I mean? I mean, after you make the measurement, you get a lot of numbers, but then you need to know which number is referenced to what vertices, right? So you need to have a way to organize this information, and the idea of this database is to help you to organize this information. Okay. So this is what I did for dealing with this point. Okay, and let's go back to the database. Now you have to, for each team, you have to divide your zone, the area that you are responsible for, into parts, right? You are not going to do it as one piece, okay? You have to divide it into components, okay? And then each component need to lock on some of these grid intersections. Okay. So for load 300 model, every component has to get a record here. So for example, there is a, let me add a new one. Okay, parent ID, for example, if this is for group A, then you click here, and the element ID automatically register it as zone A11, and this number is created automatically. Okay, and then the surface represent the geometric entity representing this component. You export it as a Rhino file and then attach it, drop the file here, and also create a 3D mesh file and then put it here. Okay, so this is for load 300. Okay, and I have extended the homework, so you need to finish this in 2 weeks. Okay. And after you have divided all the load 300 panel, okay, component, for example, if you design a component, okay, like this one, okay, maybe you have some fold, okay, like this, and you want to fix it onto the laminar structure at some good intersections, okay? But this one consists of many parts, right? Maybe it consists of 3 small pieces, and each of these has to be fabricated. It has to go to a CNC machine and they cut. Maybe this one is aluminum, and this one is another piece of aluminum, and this one is a piece of glass. Okay? So you have to, first, for low 300 model, maybe you make a rough shape, okay, to represent this panel. Maybe the overall shape, but not including the details for low 300 panel. And for each panel, you need to create a record in low 300 table, okay? And then after you have done this, you have to further refine this model into individual pieces for fabrication. So for example, you need to draw a shop drawing for this panel, right? Because the factory has to cut it exactly as the shape that you draw. So this is a shop drawing, and maybe somewhere you need to punch holes or whatever because you want to make the lock. So you draw a shop drawing for this panel, and then maybe a shop drawing for this panel, or if your way of fabrication is you cut a piece of aluminum sheet like this, and then you ask the factory to fold this line for some certain degree. Okay, so you need to do this as a shop drawing and then put it on the database. Okay, after you have done this 300 model, then I will show you how to add this information into the database. So after you have finished the low 300 table, we have the rough shape of it. And then we move on to the 400 table. We need to have 3D model for individual pieces based on how you are going to fabricate it. Okay? If this is one whole piece, maybe you did it with 3D printing machine. So then it's fine, then this is one piece. But if you have to join different parts to make the whole component, then you have to have individual model for each of the parts, right? So this is aluminum and this is glass, and you have a frame, okay? And the frame is again aluminum extrusion. And then this frame consists of maybe 1, 2, 3, 4, 5, 6, 7, 8 pieces. Then you make each individual pieces as one model, and you draw shop drawings for each of these. Then with all this information, the fabrication company, the fabricator, they can do it precisely. Okay? Okay, so I want you, I know this, even to me, is complicated, okay? But we want to experience the process from design to fabrication and how to handle all the information along the process. Okay, and now I have to say that we are actually doing some experiment, okay, using database to manage all this information. Okay. This is not current practice. If you go to the construction company, you can ask Boris. You are not doing it like this, right? You are maybe the design team of this global company. They have to make drawings, they make thousands of drawings, and then now what they do, they use the internet hard disk drive or send emails, the design team, they make these shop drawings and then how they do? Google Drive. Okay, they use Google Drive, and then maybe they have to write emails to tell the company, the factory people, and then where to get these files. Okay, and then make the correct ID for these files. Okay, and the factory people, maybe they have to open the drawing and then try to find out manually which shop drawing is corresponding to which panel. Okay, and when the structure is not so complicated, it is okay, it works this way perfectly. But when you get more and more complicated construction, especially for curved surfaces, each panel is individual. Each panel is different from the other one. And there are tens of thousands of panels. How are we going to organize it this way? Okay, so we need to move on. And in the school, we can try more advanced or try to experience some, maybe we are able to, we're going to find a better way, okay? So I want you to know the idea, and we use this L table to somehow to practice this. And right now, I have to say that it's kind of, not so convenient, okay, because we don't have the adequate tool right now, okay. But there are techniques. If we know how to work it out, then the adequate tools can be developed. Okay, so maybe we take a break for 5 minutes, and then the second part I want to talk about kinetic structures, because in the course schedule, I think for the course introduction, I put this week here, course introduction. Kinetic system simulation, okay? And actually we should have talked about curved surface analysis, and okay. There is a plugin called Ngrams. It is a plugin help you to take care of the mesh structure, but I haven't got the time to talk about this. And this week we have the third part, case study from you, and the second part I want to share with you something about kinetic system. Okay, good. We take a break for 5 minutes.
Just check. It's just a single number. Yeah.
Hmm.
Okay.